simple harmonic motion, oscillatory motion, and periodic motion. Before starting the lecture, click on the subscribe button and get access to our 100 of conceptual lectures for free. Firstly, understanding the concept of periodic motion. The motion of an object that repeats its path regularly after equal interval of time is called periodic motion. For example, motion of the mass attached to elastic spring. We know that this mass repeats its back and forth motion over the same path after equal interval of time. So it is in the periodic motion. Secondly, motion of the earth around the sun. We know that the earth moves over the same circular path and repeats its motion after equal interval of time. So it is also in the periodic motion. Thirdly, motion of the hands of a clock. And fourthly, motion of the pendulum. These are the different examples of periodic motion because they move and repeat their respective motion over the same path after equal interval of time. Now let me teach you that periodic motion is further divided into two types of motion: oscillatory motion and non-oscillatory motion. Here, what is oscillatory motion and what is non-oscillatory motion? Well, periodic motion in which object moves back and forth or up and down from a fixed point is called oscillatory motion. Or simply you can say that up and down or back and forth periodic motion is also called oscillatory motion. For example, the motion of a mass attached to elastic spring, the motion of a simple pendulum, strings of the guitar. These all objects move back and forth from a fixed point. So they all are in oscillatory motion. While periodic motion in which an object doesn't move back and forth from a fixed point is called non-oscillatory motion. For example, motion of the earth around the sun. The earth doesn't move back and forth, but it repeats its motion on a circular path. So it is a non-oscillatory motion. Secondly, the motion of the fan and the motion of hands of a clock. These all objects move and repeat their respective motion on a circular path. So they all are a non-oscillatory motion. From these examples, we learn that every oscillatory motion is periodic motion. For example, the motion of a mass attached to elastic spring is periodic as well as oscillatory motion. Also, the motion of a simple pendulum is periodic as well as oscillatory. Secondly, we learn that not every periodic motion is oscillatory motion. For example, the motion of the earth is periodic but not oscillatory. The motion of hands of a clock is periodic but not oscillatory. Thus remember that every oscillatory motion is periodic motion, but not every periodic motion is oscillatory motion. Now, oscillatory motion is divided into two types: SHM or simple harmonic motion and non-SHM or non-simple harmonic motion. Firstly, we will understand SHM, and finally, as a bonus tip, I will give you an example of non-SHM. So, understanding oscillations and SHM. Let's consider a mass M attached to elastic spring. Now I displace this mass M from its mean position. Let the displacement of the mass from its mean position is x. Due to displacement x, restoring force F produces in the elastic spring. Let me repeat it. Due to displacement x, restoring force F produces in the elastic spring. This restoring force produces acceleration in the mass. As a result, mass moves back and forth at its mean position. Now listen carefully. If the size of displacement x of the mass is small, the size of restoring force F will also be small on the mass m. If I increase the size of the displacement x, the size of the restoring force F will also be increased. Thus, we therefore write F is directly proportional to x. Secondly, the direction of displacement and the direction of the restoring force are opposite. So I write F is directly proportional to negative x. Now to eliminate the sign of proportionality, we have to put some sort of constant. Thus we get F is equal to negative k into x. K is the spring constant. I call this equation number 1. We have learned that restoring force F also produces acceleration A and the mass m. So according to Newton's second law, we get F is equal to ma, and I call it equation number 2. Now comparing equation number 1 and equation number 2, I get ma is equal to negative k into x. Rearranging the equation, I get A is equal to negative k over m into x. We know that k is the spring constant and m is the mass attached to the elastic spring. These both quantities are constant. So acceleration A of the mass m purely depends upon its displacement x. And also remember that the direction of acceleration will be opposite to the direction of displacement. Hence, we define SHM or simple harmonic motion as when force on oscillating object is directly proportional to the displacement from its mean position is called SHM. Let me repeat it. When force on oscillating object is directly proportional to the displacement from its mean position is called SHM. Also remember that in SHM, acceleration is also directly proportional to displacement. Therefore, in oscillatory motion, if force is directly proportional to displacement and acceleration is also directly proportional to displacement, we also call this oscillatory motion as SHM or simple harmonic motion. Remember these two properties of the simple harmonic motion. Finally, as a bonus tip, let me teach you that not every oscillation is SHM. For example, when you drop a ball from a certain height h on a perfectly elastic and plane surface, the motion of the ball is oscillatory but not SHM. It is because the restoring force on the ball is provided by its weight W is equal to mg, not by the vertical height h. This was all about periodic motion, oscillatory motion and SHM.